As I was saying, thanks everyone for being here, and also thanks to the organization for inviting me. My name is Valter Balegas, and I'm CTO at Electric, and I'm here to talk about developing local first applications. So before I go into the details of the talk, technology never helps when it needs. Before going into the details of the talk, let me just briefly present the company. So I'm a researcher of background. I did 8 years of research here in Lisbon. I work with Nuno Preguiça and Mark Shapiro, which are the inventors of CRDTS. So my background is mainly distributed systems. Later, I left the academia and joined industry. I worked on a couple of startups. Then I moved to Oracle, where I was working in MySQL as a service. My co-founder, James Valter, is a serial entrepreneur. He has won a couple prizes and have created companies in the values of hundreds of millions of euros. So we met through our board, and James was trying to create a company around CRDTS technology. I also had lots of ideas how to bring CRDTS technology into industry. So we decided to create the company. Our focus was in developing applications with high quality experience, particularly minimize the latency and increase the interactivity of applications. We got some funding in the beginning of the year. We funded the company. We gathered together a company with highly expertise people. We have people from Stockholm to Istanbul. Most of our background is distributed systems. People also have background on Elixir and Erlang. We are able to attract talent from high companies, enterprises like Cisco and Couchbase, but also from people from more of a startup background. We also have Purva Gunjar, which is in a Zoom with us today. Also, James is also in the Zoom, so he's probably saying hi to all of you, although you don't see it. She's handling the growth of and community on the company. She's based in San Francisco, and we also have the advisory board, which are technical advisors, Nuno and Mark, which are creators of CRDTS, and also Annette Yunusa, which is a prominent researcher in the area. So this is a presentation of the people. Let's move into the subject matter. So I'm going to start with a statement that probably everyone in the room agrees. Developing applications is very difficult, and we all want to make applications development easier and a more enjoyable experience. However, users require high-quality user experience. This means that applications need to be fast, responsive, and at the same time provide high degrees of interactivity. And this is not always easy for developers to build, because as each generation of application comes out, more things developers have to do, more concerns they have to handle. And all of this complexity leaks back to the application developer. So I'm going to talk about the few sources of complexity in applications. First and foremost is the network. Even if in developed countries we believe that network is always pervasive and it's continuing to be more available over time, the truth is in our daily routine, sometimes internet just disconnects. Either because we are driving the car, we enter the tunnel, or just entering from the street into the building and we just lost connectivity because we just connected to the local Wi-Fi. So whenever the internet goes down, applications suffer with that. Applications are not really good at handling network connectivity, so state of connection goes down. For application to recover, we just close the application and open it again. But this is not an example of a good experience. The second source of complexity is state transfer. We are building applications that are sitting in the palm of our hand, but the data is stored in hundreds of kilometers away in the data store. So there is APIs with which we have to contact to get the data. And data is transferred from a database into our application. There's a lot of transformations, and developers have to think if the logic executes on the device or the logic executes on the server. And there's a lot of impedance between managing the data in a local device and managing the data on the servers. So again, even though we have good infrastructures and frameworks to handle this, it's not always transparent to deal with state. And third thing is one additional concern that developers nowadays need to handle. So we see applications becoming more interactive, and particularly in the multiplayer space. Today, we want applications that each user in different device can be collaborating together on the same documents, and they have response about the interactions that the other users do in documents. This is an example of a new concern, and new applications need to handle this. And there's already frameworks and platforms that help developers handle these things, but again, is another source of complexity that developers need to handle. Now, you can pick different software development paradigms, and they will handle these complexities with different trade-offs. So picking the example of a classical client server. We have a single server sitting in somewhere in the geolocation of the world. There is no state transfer because the rendering and the logic is processed in the same server. It potentially can be good to create a multiplayer experience because all requests are going to the same server. However, we have the network in the middle. And even worse than that is that if this is a single server and we are providing a global application, users will have different experience depending on the distance to the server. So this is an option that is not very good to provide good interactive applications. In the other extreme of the spectrum, we have client-centric. This is the kind of JavaScript front-end platforms. And in this case, there is no networking part. It's still network exists to transfer the data, but when you interact with the data, we are interacting against a local store. The problem is that you have to deal with state transfer for everything that you do, because all the data is remote. We need to fetch the data, transform the data, decide what operations are executed locally and operations are executed remotely. It's more difficult to create a multiplayer experience because there is no server helping on the coordination of requests from multiple users. And then there are many points in the middle of the spectrum, and particularly server-side rendering, which is very popular with LiveView and other frameworks. They don't need to handle state transfer because you move the rendering and the logic to the server. Potentially, they are good to implement multiplayer experience, particularly if they are supported by edge infrastructure that handles the coordination of state across machines. But again, they have the network in the critical path. So if you have network hiccups, your experience will suffer with this. Obviously, I'm mounting the case for a new paradigm that solves all of these complexities. And this paradigm is local first software. This is not recent in academia, but has gained more traction in industry with papers from Ink and Switch that discuss this model and describe its characteristics. So the fundamental idea of local first software is that you don't program against an API, you program against the database that sits on your device. And this solves the problems that I was mentioning before, because there is no state transfer. You program directly against the database. Potentially, the network is also easy to handle because you don't need to write failure path code. You don't need to be concerned about the state of the network because it's abstracted away from the development. And it also has nice properties for the user. It is more privacy preserving because the user owns the data. And it's also more efficient in terms of computation because you can use your local device to do the computation as well as the storage, and we don't need to pay the cloud for having these commodities. However, local first software comes with complexity on its own, which are, in my opinion, are even more difficult to solve than the problems that I mentioned before. So the two main difficulties with local first software is that the model is described as being poorly peer-to-peer. The expectation is that users connect to each other in a peer-to-peer fashion to exchange data. So this is probably a big barrier for developing large-scale applications, which is not a very pragmatic solution for industry. And the other thing is that they need a convergent data model. Not all databases provide this kind of semantics, particularly if you use a SQL database, it's not convergent by default. What I mean by convergent is a database that is able to take updates that users execute in multiple devices and somehow converge the changes in a non-conflictive way. So if two persons modify the same document, instead of popping up, look, there's a conflict we need to solve, we want these conflicts to be solved automatically. Particularly, ensuring convergence is not enough to provide more sophisticated invariants like those we need in applications, like referential integrity, unique constraints, and those types of checks. So the data model that we require for doing local first, there's a bit of friction with requirements that developers actually have when developing real-life applications. And because local first is being used by only a few companies successfully, it doesn't have very mature tools that are required to handle pragmatic issues that developers have to handle every day. One of these issues is migrations. I mean, the scheme of applications evolves over time, and then how do you do migrations in a fully distributed system that is not where data can be in one version, the software can be another version? How do you solve these problems? And the last thing is not having access to a global store. So even if users own their data, to develop real-life applications, there are data that is not particularly owned by the user, but owned by the service. So how can users access this kind of data in a way that is compatible with the principle of local first? So this is the issues that we are trying to solve with Electric. We are the missing piece to make local first software a paradigm that is viable to build industry-grade applications. And how we do that? So if you want to scale the code, be free, but it will appear multiple times in our conversation. So ElectricSQL, we are not trying to ask developers to use a different stack, because this is local first software. You're supposed to use the tools that you like to develop an application. So you just want to develop against a local database. So how do we do this? The way we do this is that we provide a replication layer. So I was saying before that the local first does not prescribe what is the semantics for synchronizing the various devices. We are giving you that layer. And the replication layer encapsulates all the complexity with the data model, with network and state transfer. This is our replication layer works as a plugin for your existing stack. The only requirement is that your local database is a SQLite database. We are picking up SQLite as a starting point because SQLite works across web, mobile, and edge servers, and it's a popular choice with developers nowadays. So we are banking on that popularity. Besides the integration with SQLite on mobile devices, we also have a global geo-replicated Postgres store. And the idea is to provide this global data that I was mentioning before. So developers can also use this type of data in a highly available way distributed across the globe. So we really want to make life easy for developers, and we think this is the way of driving adoption. So we're providing our replication service as a managed service. Our code is all open source, so developer can run the infrastructure of the replication if just trying out. But the idea is that users that want to use Electric just subscribe to the service, create an application, get the credentials, configure the credentials in a database, and replication automatically starts between devices of the same user or between devices of different users if they share data between them. I was mentioning that we are doing this for SQLite and we are focusing on the SQL engine, but nothing prevents us from supporting other query languages. So we are trying to add support for graph and also object-oriented interfaces. This is because our replication protocol is actually agnostic to the query language that you use. It's a standard protocol that just replicates transactions. We use a data model based on CRDTS with integrity. And this is important. I'll cover a bit more later because CRDTS only helps so far as giving convergence, but to ensure the integrity, we need to combine the semantics of the data model with the replication protocol that we use. And we have an integrated solution that solves this problem. Now, I was saying that local first is all about privacy, and now I'm saying that I'm using the cloud. It's a bit contradictory, but in fact, it's not, because all data is stored on a device and the user only shares the data that he wants to share. Even if he uses the cloud to store some of his data, because the user is concerned with the backup, doesn't want to lose the data if he loses the phone, all the data that is stored on the server can be encrypted and stored safely on the cloud. Because the data will only be used by client-side databases. There is never any compute being executed against the data that is stored in the cloud. So it can be completely encrypted and opaque to anyone operating the system. Also, we provide a solution for doing migrations. We call it over-the-air migrations. Basically, we rely on our replication protocol to propagate new schema versions. And we have adaptation, transformations that we can do on the data that is coming to adapt to the local version of the code. So we handle the problem of mismatch between version of code and version of data by providing transformations through our replication protocol to adapt data on the fly. So I'm going to talk about the architecture of the system. I'm going to show how we transform a local SQLite database into a store that can be used with our replication system. I'm going then to talk about the infrastructure that we use, and this is the backend that is developed in Elixir for propagating data across multiple devices. And then I'm going to show about the last mile, how we deliver information back to the application that the user is using. But before that, I want to make some introduction about the technology that we use. So how many people in the room knows about CRDTS? Okay, I see a few hands in the air. That's quite nice. Some time ago, it would be much less, but particularly with Elixir community, it's becoming more popular. And so what are CRDTs? CRDTs are conflict-free replicated data types. So this is data types that are prepared for creating asynchronous applications. So we can have multiple users updating the same structure. And when the state of these objects are exchanged, there is a merge mechanism that is going to combine the changes of the users into a single value. Suppose that multiple people increment the counter, we can take the number of increments that each user has executed, merge it together. So say each user incremented 2, then the resulting value is 4. And there are many flavors of CRDTs. The most common and most widely known is state-based CRDTs, and these are those that uses this merge mechanism to combine multiple copies of the same object. This maps very well to replicated systems. But another solution, and one that we use in our system, is operation-based CRDTs. With operation-based CRDTs, instead of propagating the whole state of the object, we just propagate the mutations to the object. So if we incremented the counter, we propagate the increment and propagate them across the different replicas. So CRDTs are widely popular in local first approaches, but they don't solve all the problems. They can ensure your convergence. They give you automatic conflict resolution so that you don't need to write conflict resolution logic. And they can enable collaborative applications and have this feedback of presence and the other techniques that are used for building collaborative applications. But they don't give you guarantees across the single boundaries of an object. So if I have a constraint that I want to ensure that the sum of the balance of my savings account and my deposit account, it's an invariant that spans multiple objects, and this cannot automatically be ensured with CRDTs. So this is one difficulty of doing local first, is that you not only need CRDTs, but you also need a replication protocol that ensures consistency across objects. And this is what we do. Actually, we are able to enforce integrity constraints of SQL databases. I mean, check constraints, like a value cannot go below 0. We ensure uniqueness, and also we ensure referential integrity, which is if there is an entity in one table and references another entity and another table, I must make sure that both entities exist at the same time. And this is all of these things that require cross-object consistency. It's not something that the CRDT solves, but it's something that the replication protocol solves. So the replication protocol that we use is the Q protocol. The Q protocol is a highly available consistency model. This is based on transactional causal plus consistency. I'm going to explain what the words mean. Basically, it's a transactional system that allows you to execute transactions. And the causal plus means that it preserves the happens before rule. So if there are two operations that depend on each other, it guarantees that the operations are delivered to all participants in the replication system by the order in which they were executed. And the plus basically means that it's conversion, which is the properties that are given by the CRDT data model. So Untitled TB is an Erlang project. It's based on React Core, which was a popular key value store a few years ago. And React Core is just the core layer that they use for doing the geo distribution of the partitioning of the system. This is mainly has been mainly been an academic project, but we are taking the database into industry. It has been widely developed in European projects with people of the academics that I mentioned before, but also with other universities. It has been heavily tested. It's still not been submitted to Jepsen testing, but there are multiple researchers that have verified that the transactional protocol actually enforces causal consistency. So we are very confident on the success of our choice, and actually for the types of workloads that we've been testing, Untitled TV is performing quite well. So coming back to how the system works, the first thing I'm going to focus is how we transform SQLite into a CRDT database. So the idea for that is quite simple. Basically, we just do some triggers to the database that watch every change that is executed to the scheme of the application. And for each operation that is executed, we put that in an operation log. And we associate all the metadata that is necessary to produce the conflict-free semantics. We store all of this information in the log, and then we have a replication sidecar that integrates with the SQL database that the user is using. Basically, it's just a watchdog that is looking into the operation log to see if new operations appear and push those operations to our replication pipeline. The only integration that we have with the application code is actually what we call electrifying the driver, because we need to proxy the interface of the driver so that we are aware of when there is a new operation that does a mutation to the database to trigger the replication sidecar reactively. Otherwise, the replication sidecar would pick the operations, but this way it's just reactive. Okay, we actually are now studying other ways of doing the reactivity directly on the database, and if we are successful with that, we can remove all of this part of electrifying the driver. But right now, we provide a number of drivers that users can use across several popular platforms. So we have a driver for SQLite in React, we have one for React Native, and we also have one for Node.js. So I'm sorry talking about JavaScript in this context, but I promise you, we are also thinking of the Elixir community. And one of the things is our integration exactly at our initial step of the pipeline. So this is the pipeline of the upstream replication. So we have operations coming in from SQLite, and we need to propagate them to our replication system. And for that, we have a protocol. So basically, any database that fits this protocol can communicate with our replication system and propagate transactions having the properties that I mentioned across the globe. But we also have a second protocol, which I think is very interesting for the Elixir community, which is directly integrated with PG logical replication. So any database that's running in Postgres that exposes a replication stream can connect to our replication machinery. And this can give you things like active-active replication across the edge without any extra integration with support for the replication mechanism. It's all out of the box. So we have two interfaces. Right now we are more focused on SQLite, but the idea is that we support Postgres the same way we support SQLite, and with the same semantic of conflict-free data model. So inside our replication pipeline, we have Electric. This is our main component. It does a lot of stuff with the data that is coming in. This is written in Elixir. It propagates the operations down to Antidote, which I've explained already. Antidote has a geo-replication protocol. So we will propagate across multiple regions the data that is coming in. On the other end of the pipeline, we deliver operations to Antidote. Antidote stores the operations internally. And then we have a log tailor mechanism that is looking at the right-hand log and picking up new operations that are coming through the replication stream. So we run this for each region where we are operating our service. The log tailor will propagate operations again to Electric, and the Electric on the downstream is a bit more sophisticated than the upstream, because this is where we apply partial replication, because data that is coming in from the replication stream might not be authorized to every user. So this mechanism enforces that the data will only be delivered to the devices that have authorization to access the data. Then again, it's the same interface connecting to the database and the other. One particularly interesting point to make here is that these databases, they don't need to be connected to receive the changes. Okay, so it's just a replication protocol, and you give the pointer of the last position where you stopped replicating. So it allows resuming from a point in time to make sure you don't lose any data. You don't need to be online. That's one of the principles of local first. You can operate offline the same way as you operate online. So the last mile is how we deliver data from the database back to the front end. And for this, we also provide an integration with the front-end frameworks. Basically, the reactive interface that we have right now is working for React, but again, the idea is to provide different framework adapters that can work with different databases. Basically, the user specifies the query of data that is interested in, and when new data comes down the pipeline, there is again a watchdog that is watching if there is any data that might affect any of the subscribed queries. If there is a match, then the backend will re-execute the queries. And this is a pretty inexpensive operation because it's directly on the local database. If it sees that there are changes to the data, basically it will send that there is a change to the rendering component, and the rendering component will refresh the information within the data. So all of this flow that we've seen in the previous slide can act reactively to send data one end to the other. And it's amazingly fast. So this basically what I had to present here about Electric. So we are currently in a pre-launch phase. So we are trying to engage with developers. We have a wait list where people can subscribe and get early access to the system. We intend to start releasing access next week or the following. So if you are interested, join the waitlist. Actually, it's very good for us to have people in the waitlist so we can go back to investors and say, hey, look, there is people using it. And there is even people from Elixir, so we need more Elixir developers. So if you can go to our website, explore it, and if you think it's interesting for you, sign up. So just before going away, I would also like to spark some interest from the community. So we see some possibilities in which our system could use in Elixir applications. One is just this Postgres integration, which we think is really transparent. So any application that uses Postgres can immediately take advantage of our system. Not right now because we're still working on details, but basically my idea is just to use the code that we have for SQLite. We are going to make a native component compiled to us and load it in the Postgres. So if there's a single code base that works across different systems. And another possible interesting idea is just to provide a backend for live view applications, because the way I understand live view, it's very good handling ephemeral data, like the number of people that are currently on the system or the position of the cursors. And that information is just online information. But if you have more sophisticated data in which you want to build your application, imagine that you want to make a creativity app and you want to have the experience of very fast interaction, probably you're going to need a more sophisticated data model. And all the complexity of dealing with CRDTS is encapsulated by our system. So it just looks like a regular relational database, but in fact, it's much more than that. So that's it from my side. Thanks for listening to me. And if you have any questions, I'm ready to take them.
Any questions? I have one. Regarding the performance, you told about like do you have like a measure of the overhead it has on top of vanilla Postgres?
Yeah, so it all in each system there is not much extra processing. So I think the largest cost is just the deployment, and we use a geo-replicated deployment across multiple regions. Right now we are working with 8 Postgres locations. So all the data is executed on the local device. So from the perspective of the user, it's immediate. It's in microseconds or nanoseconds even, if the queries are fast. And then you enter the replication pipeline. It goes to the edge, only the edge server. It immediately contacts with other users in the same location, and will propagate in the best way possible across the geographical locations. Compared to other geographical database systems, Antidote is really fast because it's highly available. It doesn't use consensus in the right path, so it's very fast. We optimize, the choice of technology is optimized for speed. Although the processing costs compared to the network process, we think it's negligible.
I assume that there are two people working on the same remote database. So two people are connected to the same database and they are changing the same record. How do you ensure that the transaction will be done? Because if there is written on local database for each, what will be the remaining, the final record on the main database on the server?
So the question is, if users are writing to different databases, how can we ensure that the final data is a combination of the two? Is that so? You can never in a convergent data model, you can never ensure the definitive result. So if user makes one thing, the other user makes another thing, the only thing to ensure that only one operation or the other executes is to use some form of coordination.
Sure.
Convergent data models just try to arbitrate the result of the conflicts, and this is the semantics of CRDTS. So there are multiple semantics. Imagine if you have a set data type. If there are concurrent operations that add an element and remove an element, we can arbitrate if the add or the remove wins. So depending on the semantic of the object, the resulting value will be one or the other. But the interesting thing about combining CRDTs with the replication protocol is that we can ensure database integrity semantics, which is not natural from just converging to data.
You're blocking the state?
Sorry?
You block the state or you
No, it's convergent. So it always takes the effects of the two databases and make a single one. And for the particular invariance of the database, it has some additional techniques, which is the work I've done in academia. For instance, for referential integrity, we'll do the same idea of add wins or remove wins applied to the reference. So if someone removed an entry and the other person added the entry, we have an arbitration that either recreates the entry or removes all the dependent entries on that entry that was removed.
You provide an API to be used by the developer to ensure that the transaction will be working better than it was.
Yeah, so our system is opinionated, so because we want it to be simple, and we normally, the standard property that people want is not to lose any data. So we are opinionated about what we should do on this circumstance. So we basically recreate all of the things that were removed. But the idea is that you can provide annotations or an API to specify the concrete semantics that you do on a reference page or on a column page. But that will be a more advanced feature for more advanced developers.
What will be the cost of using this API?
The cost is that it leaks complexity to the developer. So that's why we say we are opinionated and we provide a sensible default. But if the developer needs to go into more detail, there will be options to do that.
Thank you.
We have a question on the Zoom chat. So can ElectricSQL work without the work peer-to-peer, I guess?
I think, well, I haven't thought about that because we use our backend. But the same way we provide the standard replication protocol, so our system exports data according to that protocol. So if someone implements the same interface as our protocol, it could use the front-end stuff without any problems, I guess. And you will take advantage of the CRDT semantics as well.
If there is a conflict between two different clients, does the client who lost out get feedback that they're
So So the question is, I'm just going to repeat for people online. If there is a conflict, if the person that loses the conversions gets any notification of that. Well, that's a difficult problem to identify because who wins and who loses, it's basically the arbitration of the system that decides. What we are thinking and to our reactivity layer is to give you the feedback if your operation has already been applied to the system. So imagine that you need some form of compensation in case you lose some of your data because you are the loser in the arbitration. The application can code against that occurrence. But we think that is again complexity, and we believe that all of this should be handled by the replication protocol. There was a question that side.
Yeah. So I think I heard you say back on the slides for the driver, but currently you have a proxy for any, and then you said that ultimately our goal is to get rid of this. So how will you do that? Get rid of it? So you rely on like reactive properties of existing databases?
Yeah. So it's a bit again moving our logic inside the database. So we actually started that way. The first implementation we got was an extension to SQLite that will do the propagation itself. And then because there was complications with loading the extensions in native environments, we moved away from that because it's difficult to load an extension or practically impossible to load an extension in an application in mobile, iOS or Android. So we moved away from that strategy. But what we think we could do now is come back to the extension, embed our SQLite in the application code, and then do the reactivity directly on the database. Because we already have hooks that look into the operations that are written to the database. Then we can also have hooks that say, oops, there's a new transaction. Let me propagate this to the replication line. But it's something that we removed for simplicity and integrate that driver because we think this would be a less friction path for someone trying to do an application. If we are saying developers now load custom SQLite in your application, it's more difficult. So we choose to bring this to an upper layer.
Yeah, just have a question on the other side of the spectrum. So you mentioned that you are basically looking at the right headlock and the last mile see when that is changed. I didn't get how is that? Is that like by polling or that's reactive?
Yeah, so you're mentioning this part of the pipeline. Yeah. Right now is a polling strategy, but the idea is that we can use the events on operating system to know where the file was changed and reactively propagate the file.
When you do a data migration, is it just the data and the schema, or do you also have to migrate operations? So there's going to be a lot of history.
Yeah. So the migrations. So the question is, if we do when we do the migrations, we also need to change the format of the data, or we just propagate information about the schema. So right now, the idea is that we just propagate information about the schema because this is causally consistent with the replication stream. So up to some point, that is in one version. Then comes the schema migration, and all the data from that point is in the new schema version. So when this data is going to be delivered to a device, it will see operations in the same way because you guarantee that with the causal consistency system. Regardless of that, we need to do transformations on the client side to adapt if the code is still in the old version, to use the new version of the schema.
How do you manage your resources? For instance, if you have a mainframe table, lots of rows, where and you replicate that and you get side of the client, machine and mobile, there's less resource.
So the question is, if we have a large database and we have resources in which the database doesn't fit. So this is one central question to the system, right? Because we don't want to replicate the entire database, particularly because there is my data and there is your data, and you're only interested and should only see information related to your data. So there is a partial replication system, which is applied at this layer. So that does the filtering of data based on the access that the user has to the data. But also as I was mentioning, we need a global store for the system. So this partial replication system might also work with large sets of data. So if the data is not meant to be replicated on the device, it just sits on the cloud, and the user possibly can do a smart query that it takes the result from the database, from the queries that you make, and the next time it just uses the local cache of the query that you executed. So we are thinking of an hybrid model to support these types of queries for large data. The type of applications that we envision to doing it local first is the collaborative applications. Even you can think of a Figma example, but we think that the set of data is small, and also for the online collaboration, I think the human brain cannot handle so much data. So that says that you need to be acting collaboratively online will never grow very much.
It's also locally, for instance, because you have the data locally on the device. You also order to manage the resources.
You mean how do we access a very large database in our replication stream? Yeah, so right now with the simplifications that we are doing, we are just looking at the global database, but the idea is that we possibly have multiple replication streams depending on the interests of the user.
And we have one question, I guess it's the last one from the chat. So with regard to privacy, will there be an option to specify or select regions for servers? So I guess.
So that may be a user-centric decision, right? So I might want to save my data in a European database, but don't send it to the US. We haven't thought of that case, but I imagine that if we are giving support for users to use the cloud to store data that they own, I think there is an option as well to pick the regions that they want to store data. Sorry.
You mentioned that to do a conversion to CRDTS compatible. Do you maintain 100% feature set of SQL, or are there a trade-off during this conversion that kills a few SQL features?
So right now, even if you look at TG logical replication protocol, it's already taking away some of the functionalities of Postgres. So right now, we're just concerned with propagating change sets between the devices. But over time, we think that we can increase the scope for more features that developers require.
When applying schema migrations, I imagine that you might have clients that schema migration might be invalid and others that won't. I'm thinking about indexes, for instance. So you have a technique for recording for this?
So I suppose the question with indexes actually happens with today's migrations. So you might deploy migration to a database and the index is now becoming consistent. And the good thing is that we can't rely on the local engine to solve that. So we just applying the migrations is just the same process as any regular database. So any processes that the system needs to do to reconcile the data, it will be handled automatically. But there's obviously the preoccupation with ensuring that data that is being propagated is compatible with the schema that the user knows. And if there are non-retrocompatible migrations, there needs to block the replication stream until the user updates the application. But that's the choice of the developer in the way it does migrations.
Oh, yeah. I'm sorry. Yeah.
I guess the canonical example of series. I think it's all started with collaborative text editing.
Exactly.
Yeah. I'm just trying to think. I think what certain types of apps would be written in this style, like local first. I was thinking maybe like, how would you use this to write Instagram? Maybe you post a local, but then you also subscribe some kind of replicated post.
Sorry, I just didn't get the type of the name of the
I was wondering
application.
if you could give a bit of the real world kind of example case of an app that could take advantage of this type of architecture, local first.
Yeah, actually, I think we have a very long list of applications that could be done with this. Mainly, we are thinking initially of collaborative applications. Again, take Figma as an example because everyone's talking about it now. You can have a collaborative workspace that is local first. All the logic is done on the device. The data then is converted to the relational data model, and it's possible to replicate in our system. We also think of other productivity applications or CRM applications and utility applications or applications for utility services, like someone going take the readings of electricity on the go and that kind of things. But the thing, respecting your question, I think the point is there are more sophisticated data types that don't fit so well into the relational data model. We are thinking of a sequence CRDT, which is used to implement the text editor. So we're just starting with relational databases, but we also want to make the column types that we use to be other types of CRDTs. So for instance, we are thinking of ways to incorporate auto merge in our database so that we could use JSON from within SQLite database, or we could just implement our own sequence CRDT and expose it through a new additional type, either in Postgres or SQLite.
Oh yeah, so let's thank Valter for this amazing talk.